Hello friends. Hello friends, I welcome you all to watch my new video, and in this topic we are going to cover a very important topic of that is related to Gauss law, and that is said we will find out electric field due to a uniformly charged straight wire. Okay, so what we have to do is, as you can see, that we will first define linear charge density lambda. Okay, that is denoted by lambda. Lambda is your linear charge density of a wire. Okay, and how you denote lambda? Lambda is that charge per unit length. Okay, so per unit length, what is the charge? That can be your lambda, and it is defined as linear charge density. Okay, so let's assume that this is a infinitely long straight wire, okay, which carries a positive charge. Okay, and as you can say, this is a positive charge. This is a infinitely long straight wire and it carries a positive charge, and as you can see, you have to find out at a point P. This is a point P. At this point you have to find out electric field. Okay, electric field due to this wire. So how you will calculate? As you know already that this surface will create a Gaussian surface. Okay, so if you have to find out a electric field at point P, what will happen? You have to make, okay, you have to cover this, create a Gaussian surface. This is a Gaussian surface. Okay, and this surface will have the three component. As you can say, this is first this is cross sectional view. Okay, and second one is also a cross sectional area, and the third one, this one, is a curve. Okay, so basically what is happening, suppose just imagine that there is a straight wire. Okay, and due to, just imagine that at a point P you have to find out an electric field due to this infinite long wire. So just imagine you have to draw a Gaussian surface. So what it will look like? It will look like a cylinder, and this part will be your cross sectional area. Okay, so let me tell you, suppose this is the cylinder. So inside this there is a infinitely long straight wire, and this is the Gaussian surface. Okay, so as you can say, this is cylindrical view, this is cross sectional. Okay, this is cross sectional. Again, this will be also a cross sectional, you can just imagine. Okay, now you have to find out electric field at point P. So basically you should know that as you know the Gauss law says that integration of E, okay, dot ds, okay, will give you q in upon epsilon naught. Okay, total flux enclosed by this closed surface will give you that electric field. Okay, so what is happening here? If you will see, there are three areas. Okay, this is cross sectional, and what is the electric field this due to this wire? So obviously it will be straightly this side. Okay, this side is your E. Okay, due to this. Now here also, at this point also, electric field will be in this direction, whereas as you know, for cross sectional area, this cross sectional area, your area vector, okay, you must know this area vector. Area vector will be perpendicular to this surface. You already know that for any surface, okay, plane surface like this one, area is always perpendicular to this surface. So what is the direction of area? This, okay, for this cross sectional area, if this is the cross sectional area, suppose if this is your cross sectional area, this area I am talking about, this area I have already find out that area will be perpendicular to this, okay, and for this surface cross sectional area, what will be the area vector? This side, okay, whereas your electric field is in this direction. So and for this curved surface, you can see the cylindrical surface, and what is the we will call it curved surface. So what is the area vector here? Here also the area vector is this. This is your small area, okay, we have assumed a small area ds here, okay, and this area, as you can say, is its direction is always perpendicular to the surface. So here you can see that for cross sectional area 1 and 2, okay, cross sectional area 1 and 2, your electric field, okay, here also you can see this is your electric field and this is your area vector, okay, we call it by this one, or your unit vector, means this is the direction of your area, okay. Now as you can see that for curved cross sectional area 1 and 2, electric field and your area is making 90-degree angle, okay. So we will note this cross sectional area is making 90-degree with area vector, this with electric field, okay, electric field due to a infinitely long wire, okay, and this area, this cross sectional area is making here E, and your this area has the same, means they are parallel, okay, electric field and area here, area vector, direction of the area is in the same direction, that is it is making 0-degree curved surface making curved surface area making 0-degree with electric field, okay. I hope at this point, till this point, you are very clear. If you have any ask, please do let me know. But as you can see that this area, these two cross sectional area are making 90-degree with the area vector, and between angle between electric field and area vector is 90-degree, okay. And this curved surface, this has the electric field and area vector is in the same direction, and that is they are in parallel, so they are making 0-degree angle between electric field and the area vector, okay. So now if as you can say, if we simplify this term, what is this equation says that if you integrate a closed surface, okay, E and the small area unit, you will get the total charge enclosed upon epsilon naught, okay. Now if you will simplify this term, let's call for this area, we call, there are three surface of this, due to this wire there are three surface it is creating. So surface 1, this one I am talking about, E dot ds, and if you will remove the dot product, it will give you cos between, miss angle between E and DS. So what is the angle here? Cos 90 degree. Okay. Similarly, for area 2, I am talking about this area. Now E dot ds. Okay, I am removing this ds and cos 90 degree. Yeah, it's clear. Area and electric field and area is making 90 degree with each other. And for third area, okay, for third surface, electric field and your small area component, this one is making how much? What is the area they are making here? If you will see, cos 0 degree. Okay, equal to your q in upon epsilon naught. Okay, now this term and this term will be 0. Why? Because already you know that value of cos 90 is 0 degree. Okay, so these two terms will get cancelled and you will left with this, only this term. Okay, so what is the E dot ds? Okay, now you already know that E dot ds cos 0 is 1, so you have just this one, E ds, integration of ds equal to, this will give you q in upon epsilon naught. Okay, now we will, if we will further simplify, what is the integration of ds? This is a curved surface. Okay, and what is the area of this cross sectional? Total area, you already know that for a cylindrical surface, area is 2 pi rl. Okay, E into integration of ds. I am talking about this total curved surface. What is a area of this cylindrical surface? What will be? So it will be 2 pi rl. Okay, this will be the length. Okay, I am talking about, this is the length of the wire. Okay, so this is your length of the wire. E into 2 pi into rl. R is the radius, this one, equal to q in upon epsilon naught. Now q in, as you can say, what we can write, you already know that what is the lambda. Lambda is linear charge density and it can be given upon the charge per unit length. Okay, and if you will break, what will be your from this equation, what will be your q in? Q in you can simply write lambda into L. Okay, so we will now do this. So E into, I am writing this equation, equal to E into 2 pi rl equal to lambda into L upon epsilon naught. Okay, now your this one will get L will get cancelled. Okay, and your, if you will simplify this term, your E is what is E? Lambda upon 2 pi r epsilon naught. Okay, or we can write, I am writing this equation again here. Okay, in a better way, E is nothing but lambda upon 2 pi r epsilon naught. Okay, so this is very important equation. So what this equation says, that electric field at a point P due to this infinitely long, that is carrying, we assume that this is infinitely long wire is carrying positive current, positive charge, and we have to calculate electric field at point P from this wire, and what it will give, electric field at point P will be lambda, your linear charge density, upon 2 pi r into epsilon naught. If you already know that for lambda will be fixed, because for this wire per unit length the lambda will be fixed, so this is the constant. So how your electric field will vary for this infinitely long wire, what is the relation between E and R? Is E is inversely proportional to 1 by R. Here you can see that E is inversely proportional to R. So it indicates that as you will go further and further from this distance, this wire, electric field will reduce. So this is what this equation says. Okay, so I believe now this topic has been covered, and I hope that you are able to understand this topic now. So now we will discuss seat charge. Okay, electric field due to a seat charge. Okay, so please be continue.